Good evening, everyone. My name is Harini. I'm a PhD student at the Interdisciplinary Center for Water Research in IISc Bangalore. So currently I'm doing PMRF TA-ship for the course Watershed Hydrology offered by Professor Rajendra Prasad from IIT Kharagpur. And currently in this week, this is the fourth week, and we will be talking about the surface runoff and how to estimate surface runoff using different methods. Um, so first of all, what is surface runoff? The surface runoff is defined as the portion of precipitation that flows over the ground surface and ultimately that reaches the streams or any other water body. Okay, so surface runoff, sorry, the portion of the portion of precipitation that flows over the ground surface and ultimately reaches the streams or rivers or lakes or any other water bodies without getting infiltrated into the soil. So, as we have discussed before, surface runoff only occurs when intensity of precipitation is greater than the soil infiltration capacity. So, it occurs when intensity of rainfall is greater than infiltration capacity of soil and also when the soil is completely saturated. So in these two cases, we can see that whatever precipitation that is occurring will be converted into surface runoff immediately. And the surface runoff is mainly occurring due to overland flow and prompt interflow. Surface runoff is equal to overland flow plus prompt interflow. These two contribute to surface runoff. As we can see in this figure, we can see whatever rainfall that is falling, okay, is first converted into overland flow and reaching the streams. And also, we have also learned that there is a lateral movement of flow that occurs within the soil layer called as interflow, which also reaches the streams. So these two are the major contributors of surface runoff. Okay, and we can see that the water, groundwater and base flow also contribute to stream flow, but it takes a lot of time for it to reach the streams. And in this figure, we can see that in this figure, we can see that the complete processes that are involved in the hydrological cycle. Okay, but you can see that the major portion of it. So we can see that major portion of the processes are involved in overland flow and interflow. So whatever rainfall that is occurring is converted majorly into overland flow and interflow. And the minor amount of it is getting evaporated, transpirated, and it's going into the soil as groundwater and soil moisture. Okay. So now we will look into the different factors that affect runoff. So the first important factor is precipitation characteristics. So as we have learned that the precipitation has different characteristics like intensity of precipitation, duration, areal distribution, and the direction of the precipitation. All these will uh, mainly affect the surface runoff. And here in this graph, you can see that there is a storm A, storm C, and storm B, right? So storm B is occurring for shorter duration compared to storm C. And when you see the runoff that it is generating, we can see that the storm B is this portion and the storm C is this portion. Okay, so when you to calculate by this graph, it is clear that when the storm is occurring for longer duration, the amount of runoff it is generating is huge compared to the short duration rainfall. Okay, so duration of the rainfall impacts the total runoff volume. So this will, however, impacts the storm sewers and small culverts because they only can take some limited amount of water. But if this volume is exceeding than the capacity of these sewers or the culverts, we can see the flooding can occur. And one more characteristic is the intensity. It is clear that if the intensity of precipitation is higher, then it will result in higher volume of runoff, right? So it will intensity will influence both rate and volume of runoff. And in this storm, we can see that storm B is starting with a delay, okay, compared to storm C. So the runoff due to storm A is also generated with a delay of the same time. Okay. Then the another important characteristic is the areal distribution of rainfall. So if same amount of rainfall is distributed for a huge area, then it will contribute to lesser volume of runoff because more of the water will get infiltrated into the soil or get evaporated, right? But if the area same amount of rainfall is occurring in a small area basin, then we can see it contributes to a huge volume of rainfall. So areal distribution of rainfall will influence rate and volume of runoff. Okay. So and also here we can see that the direction of rainfall will also affect the um, rain runoff duration. And So the direction of rainfall will influence the runoff duration. As you can see in this figure, so suppose there is a storm that is moving downstream, then it is contributing to higher peak, and also the time to peak is also lower. Okay, if the storm is moving upward, then there will be rainfall in the upper direction, upstream of the basin. So it will take lot of time to reach the downstream. So we can see there is a delay in the peak, and also the volume of the peak magnitude is also reducing. Okay. So the second factor that influence the runoff is size and shape of catchment. Okay, so it will influence the runoff. If the catchment size is huge, then it will contribute to increase in runoff, and also there will be a constant minimum flow. Suppose here you can see that as the catchment size is increasing, the volume of runoff is increasing. Catchment size increases, runoff volume increases. Okay, and there will be a constant minimum flow, and peak flow per unit area will decreases. Okay, so and also here you can see that the shape of the catchment also influences. If it is a fan shaped catchment, then there will be an increase in runoff compared to the leaf shaped catchment, because here almost all these sub tributaries are of same length, so they reach the outlet point in lesser time compared to the leaf shaped. So we can see that the runoff volume is more and peak is also achieved quicker. So fan shaped catchment leads to more runoff compared to leaf shaped catchment. So the third factor that affects the runoff is the topography. So it is clear that if we, in case of steep slopes, if we have a drop of water, then it will flow more quicker than compared to a flat surface, right? So if the surface is steep, water flows quickly, so peak is high. Hello, now am I audible?
Yes, you're audible.
Okay, okay, thank you. So when there is a steep surface, we can see that there is a increase in peak. Okay, because the water will flow quickly, so the time to the water will take lesser time to reach the outlet point. So all the water from the different parts of the catchment will reach at almost same point. So we can see a high peak compared to when there is a mild or flat sloped catchment. The water will take time to reach from different parts of the catchment. So there will be a constant minimum flow, and the peak also will be lower compared to a steep surface. Okay. And if the surface is rough, then the flow will be the in the similarly, if the surface of the so, If the surface is rough, it will take time to reach the outlet. So we can see the reduction in peak compared to a smooth surface. Okay. Smooth surface, water will flow quicker. So we can see peak. Peak is higher than rough surface. So if you have any doubts, you can stop me in the middle and ask questions. So the fourth factor that is affecting runoff is geological characteristics. Okay, here you can see that if the soil is saturated, whatever the water precipitation that is falling will be converted into surface runoff. Okay, and based on the nature of the soil, the infiltration rate will depends. So it will further affect the runoff. So it will depend on the surface and second. Fourth one, we are talking about geological characteristics. Okay. So in that, we are talking about surface and subsurface soil type. So when the subsurface, based on the subsurface and surface soil type, the infiltration rate of capacity of the soil will change. So if the in case of soils like sand, the infiltration rate will be higher compared to a clay surface, right? So the volume of runoff that is generated will be lower when we compared with the soil and sand and clay type of soil types. Okay, so it will depend on surface and subsurface soil type. Okay, because more runoff is generated for low infiltration capacity soils. So I hope this point is clear. So the next factor that is affecting the runoff is meteorological characteristics. So these include, first one is temperature. So if the temperature is higher, then we see that in case of snow covered regions, the snow melt will be higher. So this will lead to increased runoff. But in case of tropical areas, we can see that evapotranspiration will be higher, which will result in decrease in runoff. Okay. So in cases of large winds, we have seen that it can lead to the what will happen when there are large rains, the precipitation, the direction of precipitation will change and all. So it may take away or bring the precipitation because the large winds can also make the clouds move, right? So it can take away or bring the precipitation. And if there is, we know that we have also seen that the large rains will increase the evaporation because it will move the water molecules away. So it will, the water will keep evaporating, and which will result in runoff decrease. And another factor is humidity. So humidity, as humidity increases, evaporation will decrease. So which in turn will result in runoff increase. Okay. So then the next characteristic is seasonal variation. This will affect the runoff. So when there is a vegetation growth, like it will occur in spring and summer season, it will influence the interception losses. So when there is vegetation, will result in interception losses. So the runoff will decrease. Okay. So also we have seen that the rainfall patterns. So in countries like India, we have seen that the rainfall is changing seasonally. So it will result in wet seasons and dry seasons. So in case of wet seasons, we see high runoff, and in case of dry season, sometimes we don't see runoff at all, or we see low runoff compared to wet seasons. So the another factor that influence the runoff is climate variations. So because of change in climate, the precipitation patterns, the temperature also changes, and we have seen that there is a shift in hydrological cycle. So this will finally influence the runoff. So climate change will alter precipitation patterns. Also, it will change the temperature and shifts the hydrological cycle. All these will influence the runoff amount. Okay. Also, when there are extreme weather events, like suppose we see extreme rainfall event, like high amount of rainfall, which has never occurred before, and there might be cases where there is no rainfall also for so many years. In that cases, we experience intense weather events, which will also impact the runoff. So extreme weather events are becoming more frequent and intense. So these will finally influence our runoff in a catchment. And the and the next factor that affects the runoff is storage characteristics. So in case of storage characteristics, we have man-made structures, okay, like dams, reservoirs, culverts, etc., which will facilitate for storage and influence the runoff. Okay. How it is, like suppose if you see there is some without any reservoir, there is flow that is occurring. We have seen suppose high amount of rainfall has occurred, then it will cause peak at some point, time t. Okay. And you can see that the peak will also reduce in case of runoff. But if there is a reservoir structure, the water will be stored in the reservoir, and we just let only constant flow to be coming out of the reservoir. So this is how the flow runoff will change when there is a man-made structure. And in case of wetlands and natural depressions, we have seen that the water will get stored in these depressions, which will reduce immediate runoff. But slowly it will get released into the uh, surface so that it will finally reach the streams. Okay. So the last factor that influence runoff is land use cover. Okay. So if the urbanization or the impervious structure surface increases, then we see that there is huge amount of runoff that occurs. Suppose if we have three cases before urbanization, after urbanization, okay, and impact of climate change and current capacity. So before urbanization, you can see that when there is a rainfall that is occurring, there will be a mild peak, and also there will be constant minimum runoff because there will be vegetation, interception losses, infiltration losses, etc. So there won't be any sudden peak. But in case of urbanization, so in case of urbanization, whatever rainfall that is occurring is most probably mostly converted into runoff. So we see there is a sudden peak that occurs within a less time interval. Okay, here suppose this is the peak, we can see this much time is taking to achieve the peak. But in case of urbanized areas, so the peak will be occurring in a short within less time gap, and also the peak magnitude is higher. So increased impervious surfaces or urbanization will lead to increased runoff. Okay. So suppose increased in case of deforestation, and once if the land is converted into agricultural land, then we see increased runoff because interception losses will be reduced, and also the evapotranspiration will be decreased, and the soil absorption rate also decreases. And in case of land cover change, based on the type of land cover it is changing, the runoff also changes. Suppose from forest area it is changed to agriculture area. We have seen that runoff is increasing. Suppose from forest area it is becoming a paved surface or concrete structures. Again, the runoff will increase because there won't be any infiltration that is occurring into the soil. Okay. And when there is a changes in the natural drainage pattern also, the runoff velocity and volume will increase. That is natural change in drainage pattern means suppose there is a concrete structure drainage that is constructed, the amount of water that is falling into that concrete drainage won't get infiltrated, and also since the surface will be smoother compared to a land surface, the velocity of the runoff will increase, and also the volume will increase. I hope everyone understood what is surface runoff and what are the factors that affect surface runoff. Now let's look into few questions related to that. So first question is surface runoff includes option A overland flow, option B is prompt interflow, Option C, both A and both B. Option D is groundwater flow. So the answer is option C, both overland flow and prompt interflow, as we have discussed earlier. The next question is surface runoff occurs when option A, intensity of precipitation is greater than soil infiltration capacity. Option B is intensity of precipitation is less than soil infiltration capacity. Option C is soil is initially unsaturated. Option D is both A and C. So when intensity of precipitation is greater than soil infiltration capacity, the runoff will occur. And also when the soil is saturated, the runoff will occur. So the option will be option A. So what are the factors that affect runoff? Option A, size and shape of catchment. Option B, topography. Option C, meteorological characteristics. And option D, all of the above. We have discussed that all these three will affect the runoff. So the option is option D, all of the above. So here in this problem, they have mentioned that the mean annual runoff of 5 meter cube per second from a catchment of area 50 kilometers square then represents an effective rainfall of. So, so we know that whatever the rainfall that is occurring after the infiltration loss, everything it will be converted into runoff, and that is called as effective runoff. So, effective runoff. So here, when we are calculating effective runoff, they are asking for the units to be in mm or centimeter. So effective runoff will be, effective rainfall will be equal to runoff. So since the unit should be in mm or centimeters, we will divide the runoff by area. So this is 5 meter cube per second divided by 50 into 10 power 6. Okay, since it's an annual runoff, we have to multiply with time. Okay, so since it's in seconds, to convert it into minutes, first we will multiply by 60. Then to convert into hours, 6 into 60, 24 hours in a day. And then we have suppose we have 365 days in a year. Okay, so then now we will have units in meters. Okay. So, by using calculator, the answer is 3.153 meters. So, they are asking for the units to be in mm or centimeter. So, into 100, 315.3 centimeters. Okay. So, the option is B. So, since effective runoff is equal to annual runoff, we are just trying to get the effective runoff values in mm. Okay, so that's why we are dividing it with area and multiplying with duration because the annual runoff units are in meter cube per second. Okay, so now let's look into the various methods that we will use to estimate the runoff. So first we have empirical formulas. So empirical formulas are mostly um, based on the region. So these formulas are developed by taking measurements like precipitation, runoff measurements, and then establishing an empirical formula between these two for a particular region. So as the region is changing, the empirical formula, the empirical relationship between precipitation and runoff will also change. So the main drawback with them is that they are applicable for only that particular region. And the rainfall runoff relationships are developed with additional fourth or third parameter. Okay. So the first empirical relationship was developed by Sir Alexander Binney for Madhya Pradesh and Vidarbha regions of Maharashtra. So here what he has done is by taking the rainfall and stream flow runoff measurements, he has given a table. Suppose we have 500 of rainfall, then he is saying that 15 percentage of rainfall will be converted into runoff. So like that he has given different runoff percentages for the annual runoff values. Okay. So the next empirical method is, sorry, Barlow's table. So he has developed this relationship for UP. He's saying that runoff is equal to Kb into precipitation. Okay. So this is R is called as runoff. P is rainfall and Kb is runoff coefficient, which is a function of the season, nature of monsoon and the catchment type. Here in this table, you can see that for the different types of catchments and the different season, the runoff quotient is given. Suppose if it is a flat, cultivated and absorbent soil, and for season 1, 2, 3, he has different runoff quotient. So like this, based on the catchment characteristics and also the nature of monsoon, we will get an runoff quotient value from the table, and by substituting it here we can calculate the runoff that can be generated. The next formula is Dickens formula. In this he has given the empirical relationship to estimate the peak runoff volume, that is equal to Q peak is equal to Dickens constant into area power 3 by 4. So this is peak flood discharge in units meter cube per second. CD is Dickens constant, which will generally vary between 6 to 30. And this is area of catchment in kilometers square. Okay. So here in this table, we can see that for different areas within India, they have given the Dickens formula. Suppose for if the region is falling in North Indian plains, the CD is 6. If it is falling in central India, the CD value will change between 14 and 28. Also, we have one more empirical formula, Inglis and D'Souza formula. This has been developed for Maharashtra. In case of Ghat roads, that is hilly areas, the runoff is estimated as 0.85 p minus 305. Okay. For plain areas, the runoff value is equal to p minus 178 into e by 2540. So based on the whether the region is falling in hilly areas or on plain surface, the type of formula to be used will change. Okay, you should keep this in mind. And there is another method from which we can estimate runoff, that is by estimating losses. So because we know that the whatever precipitation after losses is equal to runoff. So That's why we will estimate the losses and then we can calculate the runoff by subtracting it from the precipitation. So the first formula that we will be talking is given by Khosla, AN Khosla's formula. So in this he says that runoff is equal to precipitation minus losses. Okay, how we will calculate losses? So main thing is you have to remember that this formula can be applied for monthly scale only. Okay, for monthly rainfall and for monthly rainfall values we can apply this formula to calculate monthly runoff. So how we will calculate losses is formula is equal to Tm. Here Tm is temperature in degree Celsius. Okay, and the Tm should be greater than 4.5 degree Celsius. For if Tm is less than 4.5 degree Celsius, then a table is provided to calculate the losses. And once we calculate losses, we will substitute in this formula and calculate runoff. So another formula is given by David in 1983, sorry, 1938, and the formula is L equal to 0.644 P power 0.87. Here P is precipitation and let's 0.56 into 90 minus 16. T is here annual mean temperature 0 plus 0.0152 into S minus 1450 plus G. So here all the terms are in annual scale. So this is for annual scale and Kosla's formula is for monthly scale. Here the L represents the losses and once we get losses we will calculate runoff by subtracting it from precipitation. Okay. P is precipitation, T is the mean annual temperature in degree Celsius, and S is the annual duration of sunshine in hours. Okay, annual duration of sunshine in hours. And G is loss due to percolation. T is temperature, mean annual temperature, and P is precipitation. Once you know all these terms, we can calculate the losses and find the runoff values. So the third method is runoff calculation by infiltration. As we have discussed in previous lecture, infiltration can be calculated using some indices to get the average infiltration rate by indices like pi index, W index. Okay. Okay, these will give us the average infiltration rate. So once we know the infiltration rate, then from the hydrographs, what we will do? Hydrograph is a graph between intensity of rainfall and time. Okay, T intensity. Once we know the average infiltration ratio, suppose this is our average infiltration ratio, then whatever the precipitation above this, if we take the area of this part, we will get the surface runoff value. Or we have talked about this as excess rainfall or effective rainfall. Okay. So, but the problem is this is not 100% accurate because here we are considering that infiltration rate is remaining constant with time. Okay, so not 100% accurate because infiltration rate is not changing. Maybe you might have remembered that in case of hot ants or green ants, we have seen that the infiltration rate generally will reduce with time and become constant. Okay, but in the case of pi index or W index, we are keeping the infiltration term to be constant. So that's a problem. So the next method that we will be talking about is Cook's method. So in the Cook's method, we will generally estimate the peak rate of runoff. Okay, here till now we have discussed about estimating the volume of runoff, but in case of Cook's method, we will be evaluating the peak runoff rate. Okay, so it is developed by USDA, US Soil Conservation Service, and mainly we are considering that the runoff is a function of relief, soil infiltration rate, vegetation cover, and surface storage. Okay. So based on this watershed characteristics, we will assign some weights. Okay. Suppose if the catchment is steep and rugged slope, then we will have a weight 40. And if the based on the relief characteristic, and if the infiltration capacity of the catchment is slow, then we will assign a number 15. And if the vegetation cover is good to excellent, covers 90% by grass, then we will assign some number 5. Okay, for each of these watershed characteristics, we will assign some number, and once we get these numbers, we will add them to get a weight. Okay, so that weight is calculated by R plus relief plus soil infiltration plus vegetation cover plus surface storage. Okay, once we have all these values based on the watershed characteristics, we will have a weight value W. Okay, based on this W and area of the catchment, from this table we can see that the x-axis is watershed area and y-axis is peak discharge. And suppose if we have a 8 hectares of watershed and it has a W weightage value 30, then we say that the peak discharge is QP is 0.4 meter cube per second. Okay, from this table we will estimate that, and this is our uncorrected peak discharge. So to correct it, then we will adjust the peak discharge. For that, it is adjusted by some other factors like geographic rainfall factor. R is geographic rainfall factor. F is frequency factor. S is shape factor. Okay. And P is the uncorrected peak discharge that we have estimated from this table. Okay. So based on these factors, we will correct the peak discharge. And how are we calculating these factors is, suppose based on the zone which the region falls in, we have different zone factors. And based on the written period that we are considering, suppose the region is falling in zone 1 and we are estimating for a rainfall written period of 25 years, then we will take frequency factor as 1.2. Suppose if it is falling in zone 3 and we are calculating for rainfall written period of 50 year, then we will take frequency factor 1.6. And similarly, based on the length and width ratio of the catchment and watershed area, we have different shape factors. Suppose if the length and width of the length by width ratio of catchment is 3 and the watershed area is 80 hectare, then the shape factor will be 0.78 and the geographical rainfall factor is generally given. Okay, so based on these tables, we will get different factors based on the watershed characteristics, and using these factors, we will estimate the peak rate of runoff using Cook's method. So, any doubts in how to estimate the runoff using empirical formula, using by calculating the losses and by using Cook's method? Any questions? Okay. So, if there are no questions, then we will see some questions related to this. So, the first question is for Western Ghats, the relationship between runoff and rainfall given by Inglis and D'Souza formula is option A R equal to Ks into P, option B R equal to Kb into P, option C R equal to 0.85 P minus 305. Option D is R equal to P minus 178 into P by 2540. So we have seen that based on the whether okay, the answer is C, correct? Because in case of Ghat areas, this formula is used, and we have seen that this formula is also given by Inglis and D'Souza, but for plain areas. Okay, so in the next question, for a catchment in UP, India, the monthly mean temperatures are given. So they are asking to estimate the annual runoff and annual runoff quotient by Kosla's method. Okay, so here we have seen that the monthly temperature. It, also we have to remember that Kosla formula is only for monthly scale, and we have it is, and also here the monthly mean temperature and rainfall values are given. And in course law, what we are doing is we will estimate losses. That is, loss is equal to 5 into Tm for temperature greater than 4.5 degrees Celsius. And if it is less than 4.5 degrees Celsius, then we have to refer to a table. Okay, but here for all the months, we can see that the temperature is greater than 4.5 degrees Celsius. So we can estimate losses using this formula directly. So first the losses are estimated. Okay. This loss equal to 5 into Tm and calculated. So here in this case we have considered 4.8 into Tm and then calculated all this. And also since suppose if I show for the first case the 5 into Tm, that is 5 into 12 is equal to 60. Since the loss is greater than the amount of rainfall, we are just keeping here the amount of rainfall. So in case PM is less than LM, then LM is given as written as PM here. Okay. If we have higher precipitation, suppose if you see in this case, okay, the temperature is 31. 5 into 31, it is 155. Okay, approximately. And since the precipitation is 320 and the loss is 155, we are just keeping the amount of loss that is calculated using this formula. And runoff is calculated by Rm equal to Pm minus Lm. So by subtracting column 3 and column 4, we'll get the runoff values. Okay. So the total runoff will be calculated by summing up all the values, that is 171 plus 151 plus 26. So once I add that up, the runoff is 348 mm. So all the units are in mm, okay? And the runoff quotient. Runoff quotient is equal to total runoff by total precipitation, okay? So we have calculated that total runoff is 348 and the total precipitation is obtained by adding all these terms, okay? That is 40 plus 20. So that is 1060. Okay. So it is coming around 0.32. Okay. So this is how we will calculate runoff using Kosla's method, and as runoff quotient is always equal to total runoff by total precipitation. Okay. So using that, we are calculating the runoff quotient. So the next question is, for Deccan Plateau of India, the relationship between runoff and rainfall, both in given by Inglis and D'Souza formula is option A, R equal to Ks into P, option B, R equal to Kp into P, option C, R equal to 0.85 P minus 305, and option D, R equal to P minus 178 into P by 2540. Any answers? So here, as we have discussed, for English formula, the for GOT regions, the runoff is calculated using this formula, and for plain areas, this is the formula. So Deccan Plateau will for Deccan Plateau we will use this formula, R equal to P minus 178 into P by 2540. Okay. So the next question is, at a station, the storm burn of duration, 5-hour duration with intensity 2 centimeter per hour resulted in a runoff of 4 centimeter, and storm 2 of 8-hour duration resulted in a runoff of 8.4 centimeter. What is the intensity of storm burn, assuming that pi index is same for the both the storms? Okay. So how do we calculate pi index? Pi index is equal to total precipitation minus total runoffs by time. So the precipitation intensity is given. So to calculate the total precipitation, it is to be multiplied with time. Okay, 2 into 5 minus runoff is given as 4 and the duration of storm is 5. So it is 10 minus 4 by 5. So pi index is we are getting as 1.2. So since for storm 1, the pi index is 1.2, we have also, they told to assume that for storm 2 as also, the pi index is 1.2. So pi index is equal to total precipitation minus total runoff by time, right? So we know that we don't know the amount of precipitation, but the runoff is given as 8.4 for second storm and the duration of storm is 8 hours. So from this, the precipitation will be 2 into 8 plus 8.4 is 18 centimeters. To convert it into intensity, you have to divide by the duration of storm. Okay. So that is 18 divided by 8. 2.25 centimeters per hour. This is our answer. So in the next question, the observed rainfall data for successive 10-minute period of 80 minutes storm in a catchment is given in the table. So here you can see in the table for every 10 minutes what is the amount of rainfall intensity is given, and the runoff of the catchment is given as 30 mm. So R equal to 30. They are asking to calculate the pi index. So we have discussed that pi index is equal to precipitation minus runoff by time. So first what we will do is to calculate precipitation. Here they have given intensity, but we need to calculate the total rainfall value. So to calculate rainfall value, first we have to calculate the rainfall amount in each duration. So here, since we have intensity, we have to convert by multiplying it with the duration of the storm. Then we will get the rainfall amount. So that is I into T. So I will just show the calculation for first row. So since the intensity of the rainfall in first 10 minutes is 40 mm per hour, so it is 40 into 10 by 60. Here, since the duration is in minutes, we are dividing it by 60 to convert into hours. Okay, so that is 40 into 10 by 60. So it is 6.67. So 6.67 is the rainfall amount in the 10 minutes duration. So similarly, what we will do, we will calculate the rainfall amount in each time interval. So here the gap is 10 minutes, right? The time interval gap will be 10 minutes. So that's why even in the second row, to calculate the rainfall amount, it is 30 into, it has occurred, the 30 mm per hour amount of rainfall has occurred for 10 minutes. So it is 30 into 10 by 60 to convert into hours. Okay. So that is 5 mm. Since it is equally 10 minutes interval, okay, we will just multiply with all the intensity values are multiplied by 10 by 60. We will get the rainfall amount. So now to calculate the total rainfall, we'll just add this up. Okay, once we add this, what is the total precipitation that we will be getting? 70 mm. So pi index is equal to total rainfall minus total runoff by duration of storm is 80 minutes. 80 converting to hours, we are dividing by 60. Okay, it is 40 by. So the pi index is, okay, let me just calculate once again. So the total rainfall is 70 mm. 70 minus 30 divided by, that is 30 mm per hour. Okay. So since it is 30 mm per hour, and we can see that this rainfall intensity is less than 30 mm per hour. Okay. So again we will calculate the total precipitation value. Okay. So the total precipitation will be calculated by removing only this row. Okay. So the total precipitation will be, oh sorry, actually I have made a calculation error. So uh, here initially I have made a calculation error. The total precipitation is 65 mm. Okay. So to calculate pi index, it is total precipitation minus total runoff, that is 30, divided by total time. Since it is 80 minutes, we are converting into hour by dividing with 60. Okay. So the value is 26.25 mm per hour. Okay. But this is what they have given in textbooks. But generally, what we will do is, since this pi index value is more than this particular row, so in this particular row, the rainfall intensity is 20. So there won't be any runoff that is generated because of this rainfall. So then again, we by removing this particular row, what we will do is we'll calculate the total rainfall, that is 65 minus 3.33. 61.67 mm. Okay. So then what we will do is the total rainfall is 61.67 mm minus total runoff by, here this 10 minutes duration is not giving us runoff. So the total time is for the storm will be 70 minutes divided by 60. 51.67 divided by, so once I do calculator, it's 27.14 mm per hour. So this will be our uh, pi index value. So the answer will be 27.14 mm per hour. Okay. I hope this calculation is clear. So whenever we are calculating pi index, the pi index is equal to total runoff minus, so total rainfall matlab like effective rainfall minus runoff by total time. Okay. The time of effective precipitation. So initially what I was doing is I was calculating the runoff amount by multiplying time to the intensity values that they have in the given in the question. And once I get the rainfall amount in each time interval, I have summed it up to get total precipitation. So I have used this formula pi equal to precipitation minus runoff by time to calculate the pi index. So the pi index that in initial iteration I got is 26.25 mm per hour, and have seen that in all these rainfall intensities are greater than 26 mm except in this case. Okay, at that 70 minutes interval. Since the rainfall is less than 26 mm per hour, this will not contribute to the runoff. Okay, so that's why when again in next iteration, to when I'm calculating the pi index, I'm removing this particular row. Okay, so then I will calculate again the total precipitation, that is effective precipitation, and subtract it with runoff divided by total time of effective precipitation. Here, this 10 minutes is not contributing to the runoff. So that's why total 80 minutes from that I'm subtracting this 10 minutes to get 70 minutes divided by 60 I'm doing to convert into hours. Okay. After this, finally, I got that precipitation value is in between is sorry, the pi index is equal to 27.14 mm per hour. Okay. I hope this is clear. And coming to the next question. So, for a watershed, the peak runoff rate for a written period of 30 years by Cook's method is uh, 5 meter cube per second. So the runoff volume is given as 5 meter cube per second for a written period of 30 years. From the geographical rainfall factor, frequency factor, the geographical rainfall factor R is, sorry, this I'll keep as QP is 5 meter cube per second. Geographical rainfall factor is 1.15. Frequency factor is 1.6 and shape factor is 0.71 given respectively. The sum of the numerical values W assigned to the various characteristic of watershed is 60. So what is the area of the watershed? So here we know that QP is equal to P into R into F into S. So QP they have given us 5 meter cube per second. So 5 equal to uncorrected peak flow into 1.15 geographical rainfall factor into frequency factor is 1.6 into shape factor is 0.71. So the uncorrected peak flow is 5 divided by into. So by using the calci, I got the uncorrected rainfall is, sorry, uncorrected peak runoff rate is 3.83 meter cube per second. Okay, from this table, from this chart, if when the peak flow is 3.83, the value, the line will be around at this range, and we know that W is given as 60. Okay, we'll extend till this line W equal to 60. And once I draw a vertical line from here, okay, we will know where it is touching in x-axis to get the watershed area. So around it is touching when the area of the watershed is 30 hectares. Okay, that's how we calculate the area of watershed. So since the peak runoff rate is given and all the parameters involved in Cook's method are given, what we are doing is we are using Cook's method first to calculate the uncorrected peak runoff rate, and once we get that, using the chart for peak discharge based on the weights, we are calculating the watershed area in this problem. So now let's see, look into another method to estimate the runoff volume. So that is rational method. So in rational method, the peak runoff rate is calculated using the formula, but this is for mainly designing soil conservation structures. Okay, and the formula is goes as shown here. Peak flow is equal to C into I into A. C is runoff quotient. QP is peak runoff rate in meter cube per second. Okay, and I is intensity of rainfall in meter per second. Make sure all these terms are in the units that I'm specifying. If they are not in these units, no, then when you use this formula, the values that you are getting is not won't be also in the units of meter cube per second. And area is the area of watershed in meter square. Hmm. So there are some assumptions related to the rational method. So one first assumption is that the rainfall is occurring uniformly the for a duration of at least greater than or for at least equal to time of concentration. So first assumption is rainfall occurs at uniform intensity for a duration of at least equal to time of concentration. What is time of concentration? Time of concentration is defined as the time taken by the farthest point in the watershed, okay, the water droplet at the farthest point of the watershed to reach the outlet. The time taken by this point will be defined is defined as time of concentration. Okay, the first assumption is the uniform intensity of rainfall that is occurring should occur for a duration at least equal to time of concentration. And also the second assumption is rainfall should occur at a uniform intensity over entire area of watershed. Okay, so since this won't be exactly accurate, so this method is used for designing inexpensive structures so that the failure will be also limited in these cases. So the main parameters involved in the rational method are time of concentration. Okay, the first time of concentration is calculated as by using this formula. Okay, given by Kir Kirpich. Okay, so here L is maximum length of flow in meters and S is slope of watershed. This is given by delta H by L, where L is, sorry, delta H is the elevation difference between the remotest point, that is this farthest point on watershed, and outlet. Okay, so time of concentration is the time taken by the water droplet at this farthest point to reach outlet. Okay, so to calculate this we have a formula given by Kirchhoff. Okay, which involves terms like maximum length of flow, that is this length, and the slope of the watershed, which is calculated by delta H by L. Delta H is the elevation difference between this farthest point and the outlet point. And here we have assumption called like the uniform intensity should be occurring for a duration of at least a time of concentration. Why we are taking that is, suppose if you see in this, when we have a rainfall storm event occurring for a duration greater than time of concentration. Suppose this is the example that it has occurred for some time t, the rainfall. We can see that initially the runoff will be low and it will keep increasing and it will reach peak at time of concentration, and it will remain peak for some time during the duration of rainfall, and it keeps decreasing. So since rational method is used to calculate the peak flow, we to reach this peak the rainfall should be occurring for a duration of time of concentration at least. So that's why we are making this assumption that the rainfall will occur at uniform intensity for a duration of at least time of concentration. Then we can apply this method. Okay. Also, the next parameter that is involved in this rational method is the intensity of rainfall. How to calculate intensity of rainfall? In first week, we have discussed that for suppose we have written period and also the duration of storm. Then based on this IDF curves, intensity, duration, frequency curves, we can estimate the rainfall intensity. So suppose for 100-year written period, this is the curve, and for 2 hour duration, what will be the rainfall intensity? It is 200 mm. So like this, from intensity duration curve, intensity duration curves, frequency, IDF curves, we can estimate the rainfall intensity. So generally these curves, no, they will follow an equation called I equal to K into T power M by Tc plus A whole power M, where Kx, M and A are constants. Okay. T and Tc are the written period and the duration of the storms. And the third parameter is runoff coefficient. So this runoff coefficient is R by P, that is runoff by precipitation. The runoff coefficient is a function of surface condition and slope. Because we have seen that if the surface, based on this land cover on the surface, the runoff will change, and also based on the slope, that is if it is steep slope or mild slope, the runoff volume will change. So the runoff coefficient is a function of runoff surface condition and slope. And here we can see for different land use covers, and based on also based on the soil type and the slope of the surface, there are different runoff quotient values that have been defined. Okay, using these values, we get the runoff quotient. And in rainfall intensity, we can get from intensity, duration, frequency curves. And the time of concentration is calculated using the formula discussed earlier. So once we get all these parameters, the runoff is estimated as R to C into I into A. Okay, so that's how we calculate runoff using rational method. So let's look into few questions related to rational method. So in this question, an urban catchment has an area of 85 hectares. Okay, so area is 85 hectares. To convert into meter square, we will multiply by 10 power 4. Okay, the slope of the catchment is 0.006. The maximum length of travel of water is 950 meters, that is L equal to 950 meters. The maximum depth of rainfall with a 50-year written period is given in the table. So here you can see for 25-year written period, the max and for different duration of the storm, the maximum depth of rainfall is given. Okay. So if a culvert is designed for drainage at an outlet of this area, for a written period of 25 years, estimate the required peak flow rate by assuming the runoff coefficient is 0.3. So they are saying C equal to 0.3. So here from rational method, R equal to C into I into A. Okay. So we know runoff quotient, we know area of the catchment. To calculate intensity, what we will do is we will assume that the rainfall is occurring for a duration of time of concentration. So first we need to calculate time of concentration. That is Tc equal to 0.01947 L power 0.77 S power minus 0.385. Okay. 0.1947 L is 950. To S is so this is that is 27.39 minutes. So we assume that a rainfall is occurring for 27.39 minutes. So we know that for for 20 minutes the rainfall depth is 40 mm, and for 30 minutes it is 50 mm. So by interpolation we will calculate the rainfall depth at 27.39 mm. So I'm just using linear interpolation, that is 50 minus 40 by 30 minus 20 is equal to I minus some precipitation minus 40 by 27.39 minus 20. So P equal to 47.39 mm. Okay, here we need to know intensity. So 47.39 into 10 power minus 3 by 27.39 is in minutes. To convert into seconds, it multiply by 60. Okay. 2.88 into 10 power minus 5 mm per second. So rainfall runoff is C into I into A. Runoff coefficient 0.3 into 2.88 into 10 power minus 5. Area is 85 into 10 power 4 meter square. So that is 7.35 meter cube per second. Okay. So this will be the runoff. So yeah, everyone understood how to calculate peak runoff rate using rational method, right? So I'll just briefly tell you again. So what I did is, like, first we have all the terms: area, slope, length of maximum length of travel, and also the runoff quotient. Okay, but we don't know the intensity of rainfall. So to calculate intensity of rainfall, they have given for a written period of 25 years for different duration what is the rainfall depth. But we for rational method, what we assume is that the rainfall should be occurring for an duration of at least time of concentration. Since they didn't mention the duration of storm, I am assuming that the rainfall is occurring for a duration of time of concentration. I'm calculating the time of concentration first and using linear interpolation, and from this table I am getting the rainfall intensity for the time of concentration, and then I'm using R equal to CIF formula to calculate runoff. So the next question, in urban areas, the land use of the area and the corresponding runoff quotients are given below. Calculate the equivalent runoff. So if the surface is non-homogeneous, what we will do is we will calculate the runoff quotient by this formula. So this is called as weighted runoff quotient. AJ is the area of land cover J. CJ is the runoff quotient for the land cover J, and N is the number of distinct land cover within the watershed. So here AJ is area of land cover J. CJ is runoff coefficient of land cover J, and N is the number of land covers. So the weighted runoff quotient is, by using that formula, it is 8 into 0.7 plus 17 into 0.1 plus 50 into 0.3 plus 10 into 0.8 by total area. It is 8 plus, once I calculate that, 30.3 by 0.356 is the equivalent runoff quotient. Okay. So now let's look into another method. Okay. For estimating the runoff volume. Okay. So that is SCS-CN method. So here what it is developed by Soil Conservation The SCS full form is Soil Conservation Service. CN is curve number. So it is developed by National Resource Conservation Service or US Conservation Service. And the fundamental hypothesis involved in this is that the runoff occurs after initial abstractions. Initial abstractions means interception, surface storage, and infiltration. Okay. And the second assumption is that the actual retention of rainfall divided by potential maximum retention is equal to direct runoff by rainfall minus initial abstractions. Okay, so that is P minus IA minus VQ by S. Here VQ is the direct runoff. Okay, P is the precipitation or rainfall. And this is how we calculate the actual retention of rainfall. That is, from precipitation we are subtracting initial abstraction and the volume of runoff. Okay. So VQ is runoff volume uniformly distributed over basin. P is mean precipitation over basin. S is maximum potential retention of water. In a basin. So here also we are saying that the after initial abstraction and the whatever water is going for infiltration, the remaining water is contributed for runoff. That is VQ. Okay. By rearranging the terms in the above equation, the volume of runoff will be obtained as like this. Okay. So here they are assuming that initial abstraction is a function of maximum potential retention. Okay. And as per Soil Conservation Service, IA is equal to 0.2 S. Okay, that is initial abstraction is equal to 20% of potential maximum retention. So then once we use that, the formula will become substitute IA equal to 0.2 S. Okay, then this will be a one parameter formula where S is our parameter since we know rainfall for a basin. And this relation between initial abstraction and potential maximum storage, potential maximum retention. Hawkins has recommended something else. Okay, for in his case, initial abstraction is 5% of maximum potential retention, and for Indian conditions, they have recommended IA equal to 0.3 S, that is 30% of potential maximum retention. Okay. How do you estimate this potential maximum retention? It will be a function of soil, vegetation, land use in a catchment. Okay. So we have a formula that maximum potential retention is equal to 25,400 divided by curve number minus 254, where CN is a curve number, dimensionless. So generally for any region, the curve number value will be in between 0 and 100. When curve number is equal to 100, once you substitute in the formula, the maximum potential retention will become 0, and the runoff volume will become equal to precipitation. That is, suppose in case of paved surface or concrete surfaces, the whatever the precipitation that is falling will be completely converted into runoff. Okay, in those cases, the curve number is 100, and in case curve number is equal to 0, the potential maximum potential retention will be equal to infinity, and the volume of runoff is 0. That is most the entire precipitation will get infiltrated. Okay, so based on the soil type and the vegetation cover and also the land use, the curve number values are assigned. Suppose if you see here, in case of if the land cover is cultivated and based on the hydrological condition, whether it is poor infiltration or how, what is the infiltration, and based on the hydrological soil group, we have different curve number values assigned. Okay, so this is for non-urban areas and this is for urban areas. These are the curve number tables. Okay. And we also have like antecedent soil moisture condition. It represents the state of moisture in a particular area or catchment at the beginning of rainfall runoff event. Suppose if we have total runoff in the previous 5 days is less than 13 mm in case of dormant season, then it is AMC 1, that is antecedent moisture condition 1. So if the total rainfall in the previous 5 days is increasing, the antecedent moisture condition increasing. That is, as AMC value is increasing, the soil is becoming more saturated. Okay, so this is drier and this is wet. Okay, and based on this, we will assign hydrological soil group based on the soil type that is there in the area and also the land use cover and vegetation cover. Okay, so based on that, we will have different hydrological soil groups. and we'll get the curve number using that. So these tables are mainly for antecedent moisture condition 2. Okay. So in case if the AMC is 1, how we will calculate curve number is AMC. We have a direct table also, but generally we will use the formula. So once based on the land use, land cover and soil type, soil type, everything, we will calculate CN value for AMC2 condition. And if the AMC condition is 1, then we will calculate CN using this formula. And if the AMC condition is 3, then the curve number is calculated using this formula. So we can see that in case of as the antecedent moisture condition is increasing, the CN value is increasing. That is for AMC1 condition, the CN value is lower, and it will become increasing. Because if the soil moisture content is high, no, there won't be any infiltration that is occurring. Most of it will be flowing as runoff. So the as CN value should increase. Okay, in case of non-homogeneous, we calculate weighted CN using the formula that we have seen previously to calculate the runoff coefficient, that is CN weighted is equal to sigma j equal to 1 to n CNJ AJ by sigma j equal to 1 to n AJ. So this is how you calculate the weighted CN values. And once you know, we can use either this formula to calculate the surface runoff, or we can go graphical method. Suppose we know that cumulative rainfall value is 10 inches and the curve number for that particular watershed sorry and the curve number for that particular watershed is 60. So then what we can do is directly from the graph we can calculate the cumulative direct runoff value, that is here 5 inches. Okay, you have understood that the x-axis is the cumulative rainfall value and we have considered that as 10 inches, and these different curves will the different curve represents for the different CN values, and for CN value 60, this is the curve that we should consider. Okay, so we will just draw a vertical line and check where it is intersecting, and then draw a horizontal line to get the cumulative direct runoff values. Let's look into few questions related to SCS-CN method. So for impermeable or paved surfaces, the CN value will approximately be equal to. So we have discussed that when in case of paved surfaces, the total runoff is equal to precipitation. In that case, the curve number value will be equal to 100. Also from the table, if you see in the case of paved surfaces, and for all types of hydrological groups, the curve number value is almost equal to 100. Here we have 98, so that is almost equal to 100. And the next question is antecedents for moisture conditions are determined based on preceding how many days of antecedent rainfall? That is 5 days. We have discussed earlier. And for known CN of antecedent moisture condition 2, the CN will be uh, dash for AMC1 and dash for AMC3 compared to AMC2. So we have seen that as AMC condition is increasing, the soil is becoming wetter, okay, from dry to wet. Okay, so we have seen that if the CN value is higher, there will be more runoff. So in case of wet soil conditions, the runoff should be more. So soil moisture, soil CN value will be higher in case of antecedent moisture condition 3 compared to antecedent moisture condition 2, and it will be lower in case of drier case, because if it is low CN, that means slow runoff. So CN for AMC1 is lower, and CN for AMC3 is higher when compared to AMC2 condition CN. Yeah, in the next question, the potential maximum retention is given as 254 mm. They're asking to calculate the CN. We know CN is equal to 25,400 by S minus 254 is 25. Okay, sorry, I have written the formula wrong. S equal to CN. So it is 2500 by CN equal to that is equal to 50. So this is how you calculate curve number from potential maximum retention formula. Okay. And the next question is, among the four hydrological soil groups, the infiltration rate is highest in soil group A, soil group B, soil group C, and soil group D. So here, if you see that in this table, we have discussed that for different soil groups, the infiltration rate is mentioned. And in case of soil group A, the infiltration rate is higher, and as we proceed till to D, the infiltration rates are decreasing. So for soil group A, we have the highest infiltration rate. So the next question is, in a 350 hectares watershed, the CN value was assessed as 70 for AMC3. Estimate the value of direct runoff volume for the following days of 4 days of rainfall. So we have CN value. So then what we can do is we have to calculate the maximum potential retention using the formula. Okay. And then using this, we will calculate the volume of runoff by taking this formula. So here we are assuming that the initial abstraction is equal to 0.2s. So that is 0.2s whole square by p plus 0.2s. So using this, we'll calculate the runoff volume. Okay. So for AMC 3 for curve number value equal to 70 mm, this will be our runoff values in each case. Okay. And in the second question, they are asking what would be the runoff volume if the CN3 value are 100. So from this, okay, for CN3 equal to 70, the runoff value is 5.81 plus 0.58, that is 6.39 mm. So to convert it into volume, runoff volume, we have to multiply with area. Okay. So they said it's 350 hectares. That is into 10 power 4, it will become converted into meter square. Okay. That is 23,365 meter cube. Okay. In case of CN value equal to 20, what do we do is we will calculate first the maximum soil retention value and then we will calculate the runoff values. Okay, here also the for CN3 equal to 80, the runoff value will be, we will add all this to calculate the total runoff. That is 18.66 mm. So we can see that as CN value is increasing, the runoff volume is also runoff amount is increasing. To calculate it, to convert into volume, we have to multiply by area. Okay. So this will be our answers. The runoff volume for different runoff for different CN values. So for the next question, for a watershed of area 250 hectares equal to 250 hectares has a soil group C. Okay, the land cover can be classified as 30% open forest and 70% poor quality pasture. Assuming AMC of average condition and soil has a black. So AMC average condition means we have AMC 2 condition. So CN2 we will be calculating. Estimate the direct runoff volume due to the rainfall of 75 mm at a point. Okay. So first, since the land cover is changing, the CN values also changes. So first we will calculate the weighted CN. So here 30% that is 0.3. Okay. Is having CN value 60 and for 70% we have the CN value 86. So we will calculate average weighted CN value that is 78.2. Once we get CN value, what we will do is the potential retention value we will be calculated using this formula. It is 25400 by 70.8 mm. Okay. Once we get this, the volume of runoff is estimated as P minus. I'm considering that initial abstractions is equal to 0.2 times the maximum potential retention. Okay. So then again using this formula, what we will do is 75. So once we calculate it, the runoff amount will be 28.11 mm. So to convert into volume, we will multiply with area. Okay. Since it's in hectares, it should be multiplied with 10 power 4 to get into meter square. Okay. So that is 7.7 into 10 power 5 meter cube. This will be our answer. This is the volume of runoff that we will be expecting. Okay. So, do you guys have any other questions? So, in this lecture, we have discussed about what is surface runoff and what are the factors that affects the runoff and different methods to calculate runoff. So, if you have any questions, you can ask me. So if there are no other questions, we will end the session. Thank you for attending.